Okay, number 21 has to do with this population growth of rabbits. And so you are given this equation, the quantity T is equal to Q naught times e to the 0.005 T, where T is in years. Okay, so what is Q? By the way, don't read this as Q0. Okay, anytime 0 is a subscript, we read this as Q naught. N-A-U-G-H-T, okay, Q naught. All right, and so what happens? Well, that okay. Well, let's just plug in 0. Okay, when you plug in 0, you just get Q naught times e to the 0th power, which is, you know, this is just 1, so that's Q naught, right? So that tells you what Q naught is. Q naught is the quantity at time 0, so that's the initial population or initial value. Okay, and by the way, any kind of exponential growth will have this coefficient Q naught or, you know, whatever naught, and that is always the initial value, precisely because this part will be equal to 1 when T is equal to 0. Okay, so now the question is, the question says, explain what the Q naught is. I just did. Determine how long it takes for the rabbit population to double. We're looking for the doubling time. Now, what happens is you want Q naught, you want QT to be, by the way, that is Q naught times e to the 0.05 T, right? Okay, and you want this to be twice the original population, which you can write as 2 times Q naught, right? And then you can find out, discover that it doesn't really matter what that Q naught is, because if you're looking for the doubling time, you know, it's just both sides have Q naught in it. All right, so basically you'll end up with the exponential part is equal to 2, which means log of 2 is 0.05 T. Let's go to the next page here. So T is simply the natural log of 2 divided by 0.05. Okay, now if you had the calculator, you can calculate this. If you don't, then this is all you can do. By the way, 1 over 0.05 is 20. Okay, so this is the same as 20 times log of 2, natural log of 2. Okay, you can also write this as log of 2 to the 20th power, you know, because that's the same thing. This is a huge number, by the way, but the logarithm of that is not so big. And in fact, this is the precise answer. I will accept this. I'll accept this. If you wrote 13.86 years, then I know that you are using the calculator, which you will not be allowed to do on your test. All right, number 22. Is it possible for a function to be continuous? F continuous at x is equal to 0, but the limit of f of x as x approaches 0 does not exist. Is that possible? No, it's not possible. Why? Because for the function to be continuous, f continuous at x is equal to 0 means that the limit at 0 has to be equal to f at 0. Okay, and so that means this side exists, and they're equal to each other. So the limit must exist. It is impossible for the limit to not exist at a point of continuity. So number 22, it is impossible. Number 23, sketch the graph of a function. And I will just go ahead and write the requirements. And there are, of course, many different answers. Okay, let me write down the requirements. All right, so number 23, you have to come up with a graph of a function that is defined on this closed interval from -3 to +3. The limit must exist at 1, but it's not continuous at 1. Oh, by the way, this thing here tells me if the limit exists, it has to approach, the f of x should be approaching the same number from both sides of 1, but it's not continuous. So this criterion means that there must be a hole at 1, or what's a hole? It is a removable discontinuity. Okay, and I don't know what the hole is, where the hole is. above this point 1, maybe it's here, maybe it's here. I will just pick some random point here to have a hole. Okay, and the thing is, it has to be approaching this from both directions. Okay, all right, so that's one thing I know. It has to be defined from -3 to +3, so I will have to have a value at every single point. Infinite discontinuity at x is equal to -1. As long as you have an infinite discontinuity here, you have to have a vertical asymptote. Now it could be approaching, this way, or one side is that, the other is, we don't know if it's positive or negative infinity, but we do know that in both sides it has to approach, well, at least one side it has to approach infinity. Jump discontinuity at x is equal to 2. All right, so let's go ahead and try that. I have sort of written or drawn what happens at 1. Let's try to make this discontinuous with infinite discontinuity at x is -1. So you can kind of go this way, I guess, or go up to positive infinity. I don't care. And you could come back from positive or negative infinity. And anything else happening here on this side? Nope. Okay, so that's fine here, right? And what's happening at 2? Jump discontinuity. So let's jump like that. Okay. All right. Now, are we okay? Is it defined on this interval? It looks that way. Actually, it's not. I will come back to this point. Literally, I will come to that point. Okay. Number 2. Does the limit exist at 1? Yes. And it's not continuous at 1. Yes, that's fine. I mean, it's not continuous. There is a infinite discontinuity at -1. I do have that. And then jump at 2. I have that. So everything seems to be okay. Now, the only really picky thing here is, as it stands right now, the function is not defined at every single point on this interval, because I didn't give any definition at -1. What's f of -1? As it stands right now, there is no point. So let's just create something like this. Okay, now, because I put this little spot here, f of -1 is 1, okay, and I have the definition, right? I have to make sure that the function is defined at every single point, so I would have to have that. The answer key probably doesn't include that, but it should. Okay, all right, the very last question is number 24. I am not sure if I will require you to know the precise definition of a limit. Okay, so what we want to prove, what we want to state is the mathematical definition of the statement limit of fx at a is equal to L, okay, if and only if what, okay. And so the answer, of course, it's very difficult to understand at this point, but if you have spent time to understand it, maybe you can write that statement without, having to memorize each part of it. Some of you may have memorized every part of it. That's okay too. This precise definition of this statement, the limit of f as x approaches a is L, is as follows. For every positive epsilon given, there exists a positive delta such that whenever x and a are less than delta distance from each other, and it's not 0, that means x is not equal to a, right? Whenever this, then f of x and L are not far from each other. In fact, they are less than epsilon apart from each other. For every epsilon that somebody gives you, if you can provide delta such that, a positive delta, such that when x is within delta distance from A and not exactly equal to A, then f of x is so close to L, the limit, so that its distance from L is less than epsilon. If you can do that, then we have proved the limit is equal to L. Okay, so that does it. I have answered all the questions on practice test number 1. I hope you do well on this upcoming test. Take care. And remember, I will be available. If you have any questions or concerns, please reach out to me by email or Canvas, and I will be happy to help you.